Hello everyone, so let's continue to derive the stresses in a fluid at motion. So we talked about stresses in a fluid at rest, which was basically the pressure. And now we want to find the additional stresses due to fluid motion and deformation of fluid particles, which we show as tau ij. So we also stated that in a Newtonian fluid, tau is linearly related to the local instantaneous velocity gradient that we talked in the first lectures. For example, here, tau yx is going to be viscosity mu times partial u over partial y, okay? So this is valid in Newtonian fluids. So now let's find a general formula for tau and in these Newtonian fluids. So let's consider the case where the only velocity gradient in our fluid is partial u over partial y. So we don't have any velocity gradients other than partial u over partial y. Like partial u over partial x is 0, partial u over partial z is 0, and also the other velocities are also, their gradient are also 0. So in this condition, the only shear stress is tau yx, which equals to mu partial u over partial y, where tau yx is the stress that acts in the x direction and is associated with a velocity gradient in the y direction. So let me show this again in a better graph. So imagine you have height or y here. It could be a channel, it could be just wind, x and y. And we want to show the velocity distribution here. So the velocity, the only velocity that has gradient is u, and it's only in the y direction. Okay, so this is the velocity. U as a function of y. And now I want to investigate the stresses that are exerted to a fluid element here. So say this fluid element has dy and dx here. Okay, so let's investigate this. So I'm going to enlarge that, and let's look at the stresses that are exerted to this fluid at motion to this fluid element under this velocity gradient. So here, let's say it's the center of this, we call it O. So now I want to write the stresses in terms of the tau yx of the center. Okay, and I want to use Taylor series in order to write everything in terms of the stresses at the center of this O. So use a Taylor series expansion. So first, let's look at the viscous forces. I want to write the viscous forces in the x direction, not just the stresses, the viscous forces. So F of viscous force in the x direction here. So if you use a Taylor series, let's say for the stress here, what is this stress? This is in the direction of x and it's in the face of y, right? So this is just tau yx, but tau yx is for the center, and I have to use Taylor series to find the stresses at this distance of dy half. So this is the distance that I need to consider. So this is going to be dy half. So t by x plus partial, we are going to the, here we are going to the y in the y direction, so tau yx over partial y times dy over dt, dy over 2. This is the Taylor series. And then you also have some additional terms that I'm not going to write. For example, if you want to write it, it's going to be, it's a Taylor series, right? So you have 1/2 factorial. This was the first term. And then you have the other terms like the second gradient, dy over half squared times partial square tau yx over partial y squared. Because this dy I can assume is small, so I can just ignore the higher order terms and just stick to the first order, which is this term here. So this is going to be the stress here. And if you want to, so let me just write this. This is at O, right, at the center. So this is the stress, and if you want to find the force here, we need to multiply this by the area that is acting, right? So if this is, let's say, this is the fluid element, we have to look at 3D. So this area that we have, this is going to be dx, right? This is dy, and this is dz, right? In the other direction. And we are calculating the stresses here. So in order to, in this plane, right? So in order to find the force, we have to multiply it by the area here, which is going to be the area just here, right? Which is going to be dx times dz, right? Dx dz. Similarly, we have it for here. If we write it down, so now the stress is in the face of x and in the direction of y, right? Plus, I'm going to use Taylor series again, partial x, partial y, times now it's time again dy half okay, because I'm writing it right here. And then this now we have to multiply it by dy dz. Okay. So now let's go to the other end. So to this end and the other end, we can write it similarly, but now, let's see if I can remove it there. So here we have a tau xy again, but minus partial tau xy partial y dy half and then multiply by dy dz, and the other stress here is going to be tau yx minus partial tau yx partial y at point 0 o dy half dx dz. I think I wrote something here wrong. This should be dx. Let me see. Let me just make sure. Yeah, this should be dx. Yeah, I've written this because now when you take this dy is correct, right? But this should be dx, and also here is dx. And the reason is clear, because now we are going in the x direction right here when you want to write the other one. So you should take it this way. So I was a little bit suspicious about that, but now I can confirm. So this is the correct way of doing it. Okay, so now we have all these stresses. And I think this has also been written wrong in Smith's book. You can double check this. This has been written wrong there. So this is the correct format of that. So if you just wanna calculate the viscosity in the x direction, we are going to get these two components, which are this and this, right? Only in the x direction. So we have tau yx plus partial tau yx over partial y evaluated at O times dy half times dx dz minus tau yx minus partial tau yx over partial y at O dy half dx dz. And now these two terms cancel out. So we are only left with partial tau yx over partial y dx dy dz, which equals to what? Tau yx, we already had it from Newtonian formula, is mu partial u partial y. So it's going to be partial over partial y of mu partial u over partial y dx dy dz. So when the only gradient in the flow is partial u over partial y, and mu is constant, then F viscosity in the x direction over dx dy dz is gonna be partial tau yx over partial y, which equals to mu. I can take this mu out of this because it's constant. The viscosity, say, it's not varying. So it's going to be partial square u over partial y square. Okay. So similarly, you can do this for other directions if the only gradient, velocity gradient, is partial u partial x, meaning this is like extensional strain rates, right? Why? Because you have u, which is in the x direction, and then you have a gradient in u, so it's like it's increasing. This is like this. You have u, which is increasing, and it was small. So if you have a fluid element, it's like it is stretching, it's straining, stretching in one way, right? So this is kind of extensional strain rate. So now the F viscous in the x direction over dx dy dz you can similarly find that this is going to be partial tau xx over partial x equals to mu partial square u over partial x square. So in the general case, for velocity gradients in all directions, we have F viscous in the x direction over dx, dy, dz equals to mu partial tau xx over partial, why did I write mu here? This is going to be partial tau xx over partial x plus partial tau yx over partial y plus partial tau zx over partial z, which equals to mu partial square u over partial x square plus partial square u over partial y square plus partial square u over partial z square, which is going to be what? It's going to be mu, and this is actually Laplacian. The Laplacian of grad square u, where this grad square is Laplacian operator. Okay. So this is in a general case when we have velocity gradients in all directions. And in vector notations, so this is in vector notation, the viscous force for per unit volume for all velocity components. So this one was just in the x direction, right? Let's say for all velocity components in the x, y, and z direction, it's gonna be mu grad square Laplacian of velocity vector. Okay. So now what I want to do, we already had, if you remember, when we wrote this, this formula, the linear momentum formula, we have this divergence or grad dot of sigma, which sigma is stress tensor, right? So now we have both terms. So we have one term for the for sigma, we have one term for the pressure, and then we also have one term for the tau. So let's first write those. So sigma, if I write it in tensor form, is first pressure, which is for a fluid at rest, times I, the identity matrix, plus this tau, which is a additional tensor, additional stress or stress tensor, and this one is just pressure. So this is for a stress for a fluid at rest, and this is for a fluid at motion. So now I want to calculate that divergence. So let's see what is this divergence terms, which was on the right hand side of our linear momentum equation. So if you want to calculate this is going to be grad dot minus pi plus, instead of tau, I will just let me see. I'm not gonna write it. Let me first write it as tau, and this, the grad dot tau, if you see it here, we just calculated this, right? So for example, for grad dot this is just the divergence of tau right here. Okay, just for the x direction, in the x direction. Okay, so if you calculate it for all the components, what you are going to get, the dot of grad dot of that tensor is gonna be minus, the first term is just minus grad p, you can calculate that. And then the second term is gonna be plus mu grad square or Laplacian of velocity vector, right? So this is the viscous force per unit volume, or the stress gradient, the stress that is the grad dot of this stress term, or divergence of this stress tensor, the additional stress tensor. Okay, so this is going to be mu grad square v. And so now that we kind of solved this, we kind of found what are the viscous forces. So this is actually the contribution from the viscous forces. It's just a viscosity times grad square of v, which is Laplacian of v, right? So now we can write actually the momentum equation, complete the momentum equation in differential form. So if you remember, so this is the right hand side of our momentum equation, so let's write it down. Thus the momentum equation for an incompressible viscous fluid is, so this is the right hand side, so the left hand side we had rho dv over dt equals to, so instead of this I'm just going to use these terms that we found from here. So it's going to be minus grad p plus mu Laplacian of V. So these are the contact forces, and rho g is the body force. So the first two terms, these two, are contact forces, and this is the body force, and this is going to be our momentum equation for an incompressible viscous fluid. So this is the additional term due to viscosity that has been added. So let's see what are these terms. This one is inertial force. So the inertial force, or the inertia of fluid particles, equals to the pressure force plus viscous forces. So viscous force plus the gravitational force. So this is actually very important equation. This is the most general, one of the most general one that we learned in this course. So this is what we call Navier-Stokes equation. Navier and Stokes, they found this separately, and this is called Navier-Stokes equations. And in terms of index notation, so this is in vector notation. In terms of index notation, this can be written as rho partial ui over partial t plus uj partial ui over partial xj equals to minus partial p over partial xi plus mu partial square ui over partial xj square plus gi. Okay. So this is in terms of index notation. It is again Navier-Stokes equation, the most general equation for fluids that we learned in this course, for Newtonian fluids. And in general, if we have a compressible flow, so for a compressible, so this is for incompressible as we said here. But what if you have a compressible flow? So for a compressible flow, Navier-Stokes equation is as follows. So there will be some differences, especially for the viscous term. So we have rho dv dt equals to minus grad p, so the pressure term stays the same, but the only difference is we have an additional term because of compressibility, which is k plus mu third grad dot v plus mu, and the rest are the same, Laplacian of v plus rho g, and this term is the additional term due to compressibility of the flow. And as you can see, it is 0 in incompressible flows, since, as you see, this divergence of velocity is going to be 0. So if this divergence of velocity is 0, this term is going to be also 0. And k here is what we call second coefficient of viscosity. So the first one is mu, which is it as viscosity, and K is the second coefficient of viscosity. So this is only when we don't have this divergence, if it is not zero, which is when we don't have a incompressible flow, then you need to use this equation. So this is for special applications which are not typically in civil engineering, but in case I just wanted to give you the a general form of this, how you need to change the equations and what terms are added when you have compressible flows. Okay, so let me briefly overview what we learned today. So first of all, we wanted to talk about Navier-Stokes equation. So we wanted to drive that, and then we use again Cauchy stress tensor. So in the part for stresses in the fluid at motion, so we said the stress tensor can be a stress for a flow at rest and a fluid at motion. And in the part for the fluid for the stresses for a fluid at motion, we started with a simple case where we only have one velocity gradient in the flow, which is partial u over partial y. And based on the Newtonian fluid, we say that these are linearly related. So tau yx equals to mu partial u over partial y. And so we take a fluid element, and then we, based on using a Taylor series, we write these Taylor series expansion, the first order of that, to find the viscous force based on the value of the stress at the center of that fluid element. And we found that this is going to be partial tau yx or partial y dx dy dz, which is the volume. And based on the Newtonian fluid, this tau yx is going to be partial mu partial u partial y. And so if mu is constant and partial u over partial y is the only velocity gradient, so the viscous force in the x direction per unit volume is going to be mu partial square u over partial y square. Similarly, you can find it for the other directions, and then we found this is going to be the general form of F viscous in the x direction per unit volume. And in all directions, if you want to write this viscous force per unit volume, this is going to be the formula for that. So again, we come back to this definition of sigma. And if you get the divergence of that, or grad dot of that, so we have minus grad p plus this term, which is the viscous force per unit volume. So then we can write this momentum equation for an incompressible viscous flow, which is written here. So this is actually the Navier-Stokes equation in vector form, and this is the Navier-Stokes equation in index notation. And finally, I talked a little bit about the compressible flow. If you have compressibility, then you need to add an additional term to account for the stresses due to compressibility, due to the flow's compressibility. So I didn't drive this term, so you can actually drive this term, but this is out of the scope of this course. But actually, you can drive this by using the stress tensor and symmetrical stress tensor, second order symmetrical stress tensor that we have here, we showed, right? This is the second order symmetric tensor. And then using some other assumptions, you can actually drive this, you can actually drive this term. Okay, so I didn't go through that, but yeah, this is the general equation for a compressible flow. But these are the two main equations that we use in our course, which are this Navier-Stokes equation, which, as you see, we have this viscous term, which is additional in addition to the Euler's equation, and this is the most general formula for the momentum equation in fluids in differential form. Thank you very much.